Usually, ROMMON doesn't get very much credit unless you're trying to reset a password set on the router. So if you buy a used router, or if you walk into a situation where you need administrative access to a router and you simply don't know the password, ROMMON is what you will use to actually reset the password. Now, ROMMON stands for Read-Only Memory Monitor, and that's a term that I don't find very helpful because what it really is a very sparse iOS image that's stored in the router's read-only memory. And the primary purpose of ROMMON is to bootstrap the full iOS image from flash memory. So typically what happens is when the router boots up, ROMMON loads, it looks to the flash memory for an iOS image, it loads that into random access memory, RAM, it executes it, and then ROMMON is pretty much done. The iOS image takes over operation of the router from there. But there are a few things that can cause the router to stay in ROMMON mode. If no usable iOS image is present on the flash, that can cause the router to drop to ROMMON mode. If you're consoled into the router and you press Control Break within 60 seconds, you'll go into ROMMON mode. And finally, if the configuration register is set to boot to ROMMON, that will, of course, cause you to boot into ROMMON mode. And the configuration register, if you've reset passwords, you're familiar with that. It's simply a series of bits that's stored in the router's non-volatile RAM, and it controls some other variables such as the console line speed, and again, whether or not the router boots into ROMMON or boots to iOS. So in our case, we haven't actually done anything to cause the router to boot into ROMMON. We have not hit Control Break. So by process of elimination, we can conclude that we do not have a working iOS image stored on flash. It's missing or it's corrupt. It's got to be one of those two things. So why might we have a missing or corrupt iOS image? Well, one of the most common possibilities is a damaged or defective flash memory. Now, iOS, as I mentioned, is stored on flash memory. In newer routers, 1800 series, 2800 series, and so on, those routers use a replaceable compact flash memory card that actually plugs in to the back of the router, or in the front of the router, actually, in the case of the 2800. Now, if the iOS image is sitting on a damaged or defective sector on flash memory, the image can become corrupt or disappear altogether. And this is actually very common, especially on older routers, because flash memory simply wears out over time. But it's also possible that the memory has sustained some sort of physical damage. Perhaps the electrical contacts on the card reader have gone bad, or they've become dirty. Electromagnetic fields, perhaps from a lightning strike, can cause damage to the flash memory. Voltage fluctuations, such as a power outage or a power surge, can cause it. Even writing to the memory excessively can cause damage to the sectors. Flash memory has a limited number of times that it can be written to before some of those sectors start to wear out. So in our case, if this is really a problem, the obvious thing we need to do is replace the flash memory if that is a possibility. Now, there are a couple of things to keep in mind here. If we're working on an older router that does not have a replaceable compact flash memory card, the only option here is to replace the entire router. If we're working on a router, and in our case we're working on a Cisco 1841 router which does have replaceable compact flash memory, replacing the compact flash memory card is a long-term solution, but it's not going to help us right now. This is a production router and we need to get it back up and running right away. So, is there any hope for us? Well, maybe. The way flash memory actually works is it uses a technology called wear leveling. And when you write anything to the flash memory, the internal circuitry will try to write to sectors that have never been used. It actually tries to spread out the writes across unused sectors first. So it's very possible that if our iOS image is corrupt and it's sitting on a bad sector, we could perhaps get around those bad sectors by simply formatting the flash card and writing the iOS to memory again. Again, uploading a new iOS image to the flash and getting it on there. So we're going to actually try that in this case. We're going to upload a known good iOS image to the router. And course, we're in ROMMON mode, so we don't have many other options other than doing this from ROMMON, and thankfully ROMMON provides some TFTP functionality. If you've done iOS upgrades in the past, you've used iOS to actually TFTP an image up to the router, but in our case, ROMMON is the only option we have, and it will work using a command called TFTP DNLD, and we'll get into that and how we set that up in just a moment. Now we need a few things here. Some of these we already have. We need a server or PC that is physically connected to the router via a Cisco rollover cable. We've got that because we were able to go in and actually see the ROMMON prompt. We need a terminal emulation program so that we can actually interface with that console connection. In our case, we are going to use PuTTY. You can also use TerraTerm, which is a free Windows-based terminal emulation program. And TerraTerm has a few more options than PuTTY. It does have some file transfer protocols, such as X modem and Y modem, which PuTTY does not have. And those can come in handy if you just want to actually upload an iOS image over the console serial connection directly. We're not going to do that in this case, but it's nice to have something with that ability. We need to copy the iOS image. Since we're running an 1841 router, we want the 1841 iOS with the Advanced IP Services feature set on it. And last but not least, we need a TFTP server. And I recommend TFTPD32 or 64-bit standard edition. 32 or 64 is just simply going to depend on your operating system architecture. And in our case, we're going to be using TFTPD32 just because it's compatible with let's say we only have access to a 32-bit machine, having TFTPD32 is the safe bet. The standard edition is nice because it does not try to install as a service. We do not want this to be running all the time. Other TFTP server software sometimes tries to install as a service, and it wants to constantly be running, and that can be an issue, a security issue especially. TFTPD32 is also very lightweight. Does not take a long time at all to download, and it's free. You don't have to give your email address, and you don't have to register to download it. So now that we've got our requirements, let's go ahead and go to our server where we have our connection to the router. Now here we are in ROMMON mode again, and again ROMMON is simply an iOS. It's a mini iOS image that is stored in read-only memory. So we could probably try some iOS commands here, such as the question mark. So let's type a question mark and hit enter, and we see a very short list of commands. This is pretty sparse compared to what you might see in a full-blown iOS image. Now, the one we're really interested in is the one I mentioned earlier, TFTP download. And this is the command we're going to type to actually initiate our TFTP download. So we'll type this, and it gives us some help. It says missing or illegal IP address. Illegal IP address. So it's kind of complaining, but it's giving us some useful information here. It actually gives us two sets of variables. Required variables here and optional variables. And I'm going to go through real quick and just explain what each one of these are. We of course have to do the required variables. We have to input these required variables. But depending on our environment, we may want to actually look at some of these optional variables as well. Now the way you set these variables is you simply type the variable name, and they are case sensitive, an equal sign, and then the value, the corresponding value. So I will walk through and explain each one of these as I type them in. The IP address is going to be the IP address of the router. Specifically, it's going to be the IP address of the Fast Ethernet 00 interface on this router. Now this is a temporary assignment. This IP address is only going to be used during the TFTP connection. And after that connection is done, after we've downloaded the image, the router is going to release this IP address. So we're not changing the configuration, we're simply giving this a temporary IP address that it can use specifically for the TFTP download. So I'm going to type in the address that I've come up with for this, 10.1.1.240, and hit enter. Next I'm going to go to IP subnet mask. This is simply the subnet mask that corresponds with the IP address of the router. This is going to vary depending on your network, but in my case I'm running a 24-bit subnet mask, so I type 255.255.255.0 and hit enter. Next is the default gateway. Now, what if your router, the router IP and your TFTP server IP are on the same subnet? Well, you still have to put a default gateway in. It is a required variable, and if you don't put it, the TFTP download will not even attempt to download the image. In my case, my default gateway is 10.1.1.99. The TFTP server is going to be the IP address of the machine I'm connected to, 10.1.1.117. This is where my TFTP server is going to be running. I've downloaded the TFTP D32 software already and have it installed on here. And we're going to launch it in just a minute. But first we're going to finish putting in these variables. TFTP file. This is going to be the file name of the iOS image itself. Now remember, we should already have the iOS image stored somewhere on this machine. And in my case, I have it in TFTP root. And I'm using Windows 2008 Server, which likes to cut off the file extension and put it over here under file type. iOS images all end in a .bin, .bin, which is short for binary. I'm simply going to copy this file name here, go to PuTTY, and the nice thing about PuTTY is that if you have anything on the clipboard, you can paste it by simply right-clicking your mouse, and it will paste that in there. And now I'm going to add the .bin extension, because that is required, and hit enter. So I have my required variable set. Okay, so we're not quite ready to go yet, because let's look at a few of these optional variables. Now, why are these optional? Well, typically, the defaults, if you look at these variables, each one of these variables has a default set. TFTP verbose, for example, has a default setting. TFTP retry count has a default setting. The defaults will work in most situations. However, if your environment does not correspond to the defaults, then you may have to change some of these. So let's start with TFTP verbose. TFTP verbosity simply controls the output. How much output is the TFTP download command going to give you while it's working? The default is progress, where it simply shows you the progress of the download. So as you're downloading the iOS image from your TFTP server, TFTP download is going to print an exclamation mark on the screen to indicate a packet was received. If it times out waiting for a packet, it'll put a dot or period. If you're having an issue where you can't connect to the TFTP server and you're not sure why, you can change this to verbose, which is a value of 2. And that's going to simply give you some extra layer 2 information, such as ARPing activity. And ARPing, of course, address resolution protocol, that ties into the next one, which is TFTP retry count, the retry count for ARP and TFTP. Default is 18. Now, why might you want to change the default here? Well, if you have a slow network, or if your router or your TFTP server are connected to a switch that is problematic, or perhaps not the highest quality switch, and you are actually not receiving all of your ARP responses, that can cause the TFTP download to fail. So just to go over real quick the ARPing process, when the router is trying to connect to the TFTP server, it sends out a broadcast frame on port Ethernet, fast Ethernet 00, and it simply says to the network, what is the MAC address for this IP, the IP of the TFTP server, and it expects to get a MAC address back in response. If it doesn't receive a MAC address in a certain amount of time, it's going to time out. And after 18 of these timeouts, the default is 18, the download is simply going to fail. It's simply going to give up and quit. So again, if you have a network that, if you have a switch or something that may cause some of those ARP responses not to be consistently received, you may have to up this value a little bit. The next one is TFTP timeout. This is really a drop-dead timer. The entire TFTP operation cannot exceed this, or else it will simply fail altogether. It's unlikely that this is going to be the case, because 7,200 seconds, which is the default, is a very long time. But if you have a very slow network and a very large iOS image, it's theoretically possible you could exceed it. TFTP checksum. This simply controls whether or not the router is going to perform a checksum test on the image. Now, a checksum is essentially the result of a mathematical operation performed on the iOS image. The TFTP server, when it begins transferring the image to the router, it's actually going to run each bit of the iOS image through a mathematical operation, and it's going to come up with what's called a checksum or a hash. The router is actually going to perform that same process once it receives the iOS image, and the checksums should match. This is essentially an error detection mechanism. Since the iOS image is the same, if you put the bits within the image through the same mathematical process, you should get the same result. If you don't get the same result, it is indicative of corruption during download or some sort of network problem that causes the iOS image to become corrupt. So why on earth would you possibly want to change this and not perform a checksum test? Well, on some older routers, there is a bug in ROMMON that actually causes the checksum test to fail. So if you are running an older router, and in our case, we're running a Cisco 1841 router, I know that we do not have this particular image, but if you're on a different router and the checksum is continually failing, you may want to disable the checksum test on the image by setting this to 0. Next, fast Ethernet port. The default is fast Ethernet 00. If you have nothing plugged into fast Ethernet 00, or if you simply cannot get to your TFTP server through that port, you may want to change this to fast Ethernet port 01. In which case, here it's going to ignore that first part, that 0/ part, and it's just going to look at the very last number, which is the default is 0. So fast Ethernet 00, that is what we have connected to our network here, so we're not going to change this. And finally, fast Ethernet speed mode. The default is auto negotiate, and again, if you're dealing with a problematic switch or a switch that is older and does not handle auto negotiation very well, you may have to hard code the speed and duplex here. And of course, 0 is 10 half, 1 is 10 full duplex, 100 half, 100 full. And you simply enter the corresponding values if you need to change this. We're plugged into a fairly modern switch, so we're not going to need to change this. Okay, so we're almost ready to begin our TFTP download, but first we need to load our TFTP server. Here I have a shortcut to TFTPD32. I'm simply going to load this here. Now, once we load this, you see there are a few tabs, and the one we're interested in is TFTP server because we need a TFTP server to upload this image to the router. Up here you see current directory. This is actually where the TFTP server is going to look for whatever files the router is requesting. So in our case, we know the router is going to request an iOS image. We want to make sure that the iOS image is in the directory c/users/administrator/desktop/TFTP root. And here I'm actually in this directory and I see that my iOS image is present. And the server interface is going to simply be the interface which the TFTP server software is listening on. If you have more than one interface, you may actually have to go and manually set this. Here we only have one IPv4 interface. There are some IPv6 interfaces here, but we are not going to be using IP version 6 to communicate with the router. We're simply going to use the IPv4 address. Okay, so our TFTP server is up and running. We don't have to do anything else here. We've simply launched it and it actually comes up and automatically starts running. And in order to initiate the download, we're going to type TFTP DNLD and hit enter. And it shows us the options that we have already put in, the variables we have already put in. Nothing's changed. And it gives us a little warning. Invoke this command for disaster recovery only. Warning, all existing data in all partitions on flash will be lost, which is a nice way of saying it's going to format our flash memory card, and it's going to put the iOS image on there once it's downloaded, once it's done downloading it. So do we wish to continue? Well, yes, we do. So we're going to hit Y and hit enter. there's going to be a bit of a delay here because what it's doing is it's bringing up the Fast Ethernet 00 interface and assigning the IP to it. Then once that's done, it's going to go ahead and start downloading from our TFTP server. And here we see that it is connecting. The exclamation marks it is printing on the screen indicate that it's receiving packets from the server. So this is a good sign. Now, this is actually going to take about 5 or 6 minutes based on the size of the iOS image that we are downloading. What's going to happen is once the download is complete, ROMMON is going to run the checksum test that we had talked about earlier on the image to verify that the checksum that it calculates matches the checksum that the TFTP server has calculated. And if they match, the router will then format the flash card and copy the iOS image to it. Then the router will actually drop back to the ROMMON prompt. It will not boot it automatically. So we have to actually manually boot the iOS image by typing the boot command, B-O-O-T, and then hitting enter. And at that point, if everything has gone well, it will load iOS into memory. The iOS image will take over, it will begin executing, and it will take over operation of the router. Now, one thing to remember is that the running configuration on the router, which is stored in NVRAM, has not changed at all. It is still present, and the iOS image will actually pick that up and start using it. So we should have a fully functional router here in just a few minutes. So that's just good to keep in mind that if none of the changes we've made here in ROMMON are going to affect that configuration that is stored in non-volatile RAM. Now, once this is done, and once we have the router back up and running, we can close out of our PuTTY session, and we can shut down the TFTP server, and we should be good to go. We'll just simply perform some tests on the router to verify that we can access it, we can either telnet to it or secure shell to it, and that it's passing traffic normally. And again, in this case, it's very likely that we have a problematic or defective compact flash cards, so we want to go ahead and also procure a new replacement card just to prevent this from happening again, because there is a possibility that once the flash card starts to go bad, we may encounter more and more problems with it and perhaps may not be able to recover in the future. So it's good to go ahead and take care of that now. You can, of course, procure these cards from Cisco. You can get them on eBay. You can buy them in an electronics store. They are virtually everywhere, and they're fairly cheap nowadays. Also, the newer compact flash cards are faster. They're much faster than the older ones, and they're more reliable as well.